Welcome to Maths with EJD. In this video, I'll be talking about zero-sum games, and how to play them. So already, we've had previous videos right from the very beginning where we actually define different types of games. So as a reminder, a zero-sum game is a type of game in which the gain of one player, the gain of one player is exactly balanced by the loss of the other player. So I think this is the kind of thing that happens a lot in betting. So say you're betting that in the particular game, one club is going to win one team is going to win the other team. So and you say, okay, if the team wins, maybe each of you put down $100 each. So I mean, if the team wins, the other person forfeits. If your team wins, the other player forfeits their $100. So that means they lost their $100 and you gain $100. But if their team wins, you forfeit your $100, you lose your $100 and they gain the $100. That's a very good example of a zero-sum game. So it is a type of game in which the gain of one player is exactly balanced by the loss of the other player. So the total payoff remains constant. Total payoff remains constant. Hence, the zero sum. That's why it's called a zero sum. So it's like plus one from one side to minus one from the other side, and that balances it out. Okay. So let's imagine, uh, okay, let's just go straight and solve an example, right? Given a 2 by 2 payoff matrix, a 2 by 2 payoff matrix, which represents the possible payoffs, the possible payoffs for two players in a okay, the possible payoffs both players for both players in a two-player game. For simplicity, let's assume the following. First of all, player one, that is the role player. The role player has two strategies. Has two strategies, and strategies. These are strategy A and strategy B. Okay, and then you have player two. Player two, that is the column player. The column player also has two strategies. Two strategies. And these are strategy, strategy, strategy X and strategy Y. Okay, so the payoff, the payoff matrix for player one, the payoff matrix for player one, who of course is the role player, could look like this. Could look, I mean, instead of even doing this, I'm trying to see. Okay, let's just do it this way. The payoff matrix for both players are given as, okay, so you have player one now. This is player one here. Okay. And this is player two up here. So player one has two strategies, A, B. Player two has two strategies, X, Y. And you know, if player one wins three, it means player two loses three. So if player one loses one, it means player two gains one. If player one wins two, player two loses two. That's two comma minus two. If player two one gains four, player two loses four. So I think this is a nice way to represent the payoffs. Okay, so this is what we have, right? So for both players, those are the first values are the payoffs for the first for player one, and the second values are the values for the for the payoffs for the second player. All right. Of course, because it's zero sum, right? The value of the payoff of player one, the payoff of player two will be the negative value of the payoff of player one. So now, how do we deal with this? That's the next thing. What's the solution like? So we want to find, uh, we want to solve this game. So, and the step one is to identify the mixed strategies. Identify the mixed strategies. So of course, mixed strategy talks about randomization uh of strategies. So in a zero sum game, players can randomize their strategies using a mixed strategy. Okay. So for instance, player one, let player one randomize. So randomization simply means that the two strategies, there's no 50-50 chance. We can't be sure that the player one will use the both strategies by 50-50, right? So player one randomize between strategy A, between strategy A and strategy B with probabilities, P and 1 minus P. Okay. So let's say player one uses strategy A with probability P and B with probability 1 minus P. So this is probability for A, this is probability for B. So this is probability A, this is probability B. That's the kind of idea here. So and player two has something close to that. So player two randomize, let player two randomize between strategy X, and strategy Y with probabilities Q and one minus Q with probabilities Q and 1 minus Q. So that means that this is the probability of using strategy X, and this is the probability of using strategy Y. Okay. Of course, respectively, just like here, respectively. Okay. So the aim is to find the values, we want to find the values of P and Q that minimize the opponent's payoff. So the smaller the opponent's payoff, the better your loss, right? I mean, something like that. So you want your opponent to have negative to lose so you can gain, right? Or even if they win, they shouldn't win so much that you will really not like it. So the aim is to find the values of P and Q that minimize the opponent's payoff and maximize one's own expected payoff. One's own expected payoff. Okay, so that is the first step. So set up the mix strategy. And then the next thing we want to do is to calculate the expected payoffs. Step two, we want to calculate the expected payoff. Step two, all right. So step two, set up the expected payoff functions. Okay. And of course, that's going to be from the table, right? So see how that's going to be. So player one's expected payoff can be calculated using the mixed strategy probabilities P and 1 minus P for player one, and Q, they are both payoffs are going to, the probabilities of the payoffs for the two of them are going to affect each person, right? So player one's expected payoff can be calculated using the mixed strategy probabilities P and 1 minus P for player one, and Q and 1 minus Q for player two. So the expected payoff for player one, it is just for player one, right? For player one is, so then that starts. So we have, guess I want to switch colors here. So expected payoff for player one will be something like this. So you see, for player one, we have probability of getting these three. Okay. So we have three. Then these three here. And then we have this 3Q, then plus this minus 1. Okay, let me try to make sure this is as clear as possible. So P 3Q minus 1, 1Q, then 1 minus P. So for strategy B now, so 1 minus P, 2Q, then plus 4 1 minus P. So 2Q plus 4 into 1 minus Q. So, from all we have up here, right? We are focusing on player one, and the payoffs of player one are these three minus one, 2, and 4. So those four things now. So we have P. So that's the probability that player one gets this. So if player one gets this, player three automatically gets minus 3, right? So if we put all that together, so we have probability for strategy what for going by for strategy A now, we have that into okay. So for strategy A, we have 3 and minus 1, right? So this is 3, 3. So that's probability that player A uses strategy 1, strategy A, and player uh so that payoff of 3, right? Multiplied by Q. That's the probability that the second player rather, uses strategy X, okay? Plus minus 1. That is, this is what's happening here. So if we focus on this strategy A now, so the first part is, so with probability P, this is going to happen. And with probability 1 minus P, this is going to happen for player 1. So, and then this happens with probability Q, and this happens with probability 1 minus Q. That's basically what's happening here. So for A now, we have P multiplying 3 times Q, then minus 1 multiplying 1 minus Q. Basically, that's what's happening right there. So we have so P multiplied by 3Q plus minus 1 multiplied by 1 minus Q, as we see in that table. Then plus, this is for, so the whole of this now is for strategy A. You see, for strategy A. So you have for strategy A now probability P multiplied by 3 times Q plus minus 1 times 1 minus Q, because that's also going to, player 2 is going to have an input in that. So player 2 plays plays this 3 with probability Q and plays minus 1 with probability 1 minus Q. Then for strategy B, that's going to be 1 minus P multiplied by 2 plus 4 multiplied by 1 minus Q, basically. So let's see to that. So here now we have so 1 minus P multiplied by 1 minus P multiplied by 2Q. So this is 1 minus P multiplied by 2Q plus 4 into 1 minus Q. Okay. So 1 minus P multiplied by 2Q plus 4 into 1 minus Q. Okay, that's what we have there. So again, this is for strategy B. This is for strategy B. So again, in case that's confusing, look at it again. So for strategy A now, the probability of playing strategy A by player 1 is P. But as P is playing strategy A and player 1 is playing strategy A, player 2 is playing strategy X now. So it means P multiplied by 3 times Q plus minus 1 times 1 minus Q. Then for strategy B now, so that's 1 minus P multiplied by 2Q plus 4 into 1 minus Q. And that's exactly what we have right here. So we can try to simplify this so that we have E1 to be equal to P, this is Q now. So P into 3Q minus 1 plus Q, okay? This is plus times minus. So minus 1 plus Q right there. Okay, this is plus, or okay, let me be careful because minus can easily confuse us. This is 3Q. So minus 1 times 1 minus Q. The minus 1 can just go inside and change it over. So we have this uh, plus into Q minus 1, something like this. So we can have, so this minus affects this, so it becomes Q minus 1 like this, plus 1 minus P into 2Q, and this is just straightforward, 4 into 1 minus Q. So we can continue tidying up. So E is P into 3Q plus Q minus 1 plus 1 minus P into 2Q plus 4 minus 4Q, like this. So we have E1 equals P into 3Q plus Q, um, 3Q, have to be careful here. So P into 3Q should be minus 1 plus and minus minus. So minus 1 plus Q. Yeah. So yeah, I think that's good. So this is 2Q minus 4Q plus 4. Sure. So this is Q. This should be Q minus 1. So we are good to go. So P into 3Q plus Q is 4Q minus 1 plus 1 minus P into 2Q minus 4Q is minus 2Q. So this is like 4 minus 2Q, like this. So we can now tidy up all of this. So this part, I'm still looking at this. So this is P into 3Q minus 1 into 1 minus Q. Yes. P into 3Q, P into 3Q plus minus 1, 1 minus Q. On the other hand, 1 minus P into 2Q plus 4 into 1 minus Q. Yep. So we are good. All right. So 1 goes in. So we have Q minus 1. Yep, this minus 1, yeah, turns it over to Q minus 1. Yeah, I think that's fine. So that E1 now is equal to, we can open things up. So we have 4PQ minus P plus 1 minus 4, 4. 1 minus 2Q, that's minus 2Q. Minus P times 4, that's minus 4P. Then minus and minus is plus 2PQ, like this. So this is 4PQ minus P. 1 times 4 is 4. 1 times minus 2Q minus 2Q. Minus P times 4 minus 4P. Minus P times minus 2Q, that's plus 2PQ. So again, we can continue. E1 is 4PQ minus P plus 4 minus 2Q minus 4P plus 2PQ. So we can collect like terms so that E1, the expected payoff of player 1 is now 4Q plus 2P, 4PQ plus 2PQ is 6PQ. And then now what do we have? What else? So we have minus 4P minus 2Q. All right. Minus, this is 6PQ minus 4. Okay, this can be minus 4P. This is minus P minus 4P is minus 5P. Okay, minus P minus 4P, that's minus 5P, then minus 2Q, then plus 4. So this is the expected payoff for player 1. Okay. Now we need to, this is the expected payoff, right? So we can set up the Lagrangian for this to be able to solve, to get all the results we need. So how do we do that now? So let's go to, so that leads us to step 3. Step 3, set up the Lagrangian. Set up the Lagrangian. So we need to get P and Q. That's our goal. So to solve for the Nash equilibrium, using Lagrange multipliers, we need to maximize player 1's expected payoff, player 1's expected payoff, subject to the constraints subject to the constraints that the sum of the probabilities, the sum of the probabilities for player one and player two equals one. Okay, that's a very important constraint. So we see that for player one strategy, for player one's strategy, so P plus 1 minus P is equal to 1. I mean, that's commonsensical, because that's simply P plus 1 minus P, and this P cancels P, so everything goes to 1. So for player 2 strategy, the same thing. For player two's strategy, okay, we have Q plus 1 minus Q, which is also 1, because Q plus 1 minus Q, Q cancels Q, so everything still goes to 1, right? So we need to now maximize the player one's expected payoff. So now we want to maximize player one's payoff, player one's expected payoff, which is E1, while considering, that is E1, while considering the constraint for player two's mixed strategy. So then we introduce the Lagrange function. The Lagrange function will be L of PQ, and then lambda is the Lagrange multiplier, and the expression we have up there is 6PQ minus 5P minus 2Q. 6PQ minus 5P minus 2Q, 6PQ minus 5P minus 2Q plus 4. Plus 4. Now, that will be so we see the constraints already. We know that probability, we know that P plus 1 minus P minus 1, of course, already. You know, P plus 1 minus P is equal to 1. This implies that P plus 1 minus P minus 1 is equal to 0. So this is crucial here, because that's the constraint we have. So we now have that into the so with the Lagrange multiplier, so we have minus lambda into P plus 1 minus P minus 1. That's the Lagrange multiplier we have right there. So since P plus 1 minus P is 1, is always true, the constraint is automatically satisfied. Now we can just focus on maximizing E1. So we can say that since P plus 1 minus P equals 1 is always satisfied, Okay, let me do it this way. Okay. Since P plus 1 minus P equals 1 is always true, the constraint is automatically satisfied. The constraint is automatically satisfied. Now we can just focus and just focus on maximizing E1. Okay, so let's go for that. So we need we need to maximize E1, and it is the two parts are, we have P and Q, so we can take partial derivatives of the Lagrangian. So first of all, we can actually say the Lagrangian for E1 now. Okay, well, let's just go with what we have actually. So this is partial L, partial P. So we can differentiate that with respect to P. So if we do that, we have we know all this side automatically, this side is gone, right? Because 1 minus 1 is 0. So all that is gone. So we don't have to worry about that part. So partial L, partial P. So if we differentiate 6PQ with respect to P, we have 6Q. Then if we differentiate 5P with respect to P, we have 5. Then this no P, no P. So everything goes to 0 there. So, and then we have that. That is for player 1 now. This is for player 1. Then for player 2, we have partial L, partial Q. So we differentiate that with respect to Q. 6PQ with respect to Q will give us 6P. Then 5P with respect to Q is 0. Minus 2Q with respect to Q is minus 2. So we have minus 2 right here. Okay. So basically, we have these two. So step 5, this is step 4. So this is step 3. So we have set up the Lagrangian, right? So that's what we've done so far. Okay. Okay. Let me just take all of that to be step 3 so far. So to find the Nash equilibrium, okay. So let this be my step 3 now. Or rather step, yeah. That's my own step 4. Step 4. Solve the system of equations. We solve the system of equations. So to find the Nash equilibrium, we need to differentiate. Okay, we've done that already. Set them equal to 0 and solve the equilibrium values of P and Q. So solve the system of equations. That's what we are doing here now. So to find the Nash equilibrium, we need to equate. We need to equate partial L, partial P, and partial L, partial Q to 0. Okay. And solve for P and Q. That's what we have. So in that case, if we call this equation, let's call this equation star, and let's call this equation star star. Okay. So, or what is that even necessary? I don't think it's necessary. It's not necessary since we can reference using partial L, partial P. Okay. So partial L, partial P is equal to 0 simply implies that 6Q minus 5 is equal to 0. So that means that 6Q is equal to 5. That means that Q is equal to 5 over 6. Okay, Q is 5 over 6 easily. Then partial L, partial Q, partial L, partial Q equals 0 simply implies that 6P minus 2 is equal to 0. That means that 6P is equal to 2 and P is equal to 2 over 6 and P is actually 1 over 3. Okay, so we have those values easily. So we can say that we can say thus the Nash equilibrium, thus the Nash equilibrium for this zero-sum game is one, player one should play player one should play strategy A. Player one should play strategy A with probability. Okay, I think I'm getting ahead of myself. Does the Nash equilibrium is that okay, player one plays strategy A, player one plays strategy A, player one plays strategy A with probability, P equals, what did we get? P is 1 over 3. 1 over 3. Then player two plays strategy X with probability, 5 Q equals 5 over 6. Q is 5 over 6 as we got there. Okay. So in conclusion, right? In conclusion, uh the the okay, I mean, since we have all this now, right? We also know that from here, we know that from here, 1 minus Q will simply be 1 minus 5 over 6, and that is simply 1 over 6. So 1 minus Q is 1 over 6. Then we also know that 1 minus P is 1 minus 1 over 3, which is 2 over 3. So 1 minus P is 2 over 3. So in conclusion, right? Yeah, instead of, let me not duplicate this. Let me not waste time just trying to duplicate this, right? Let me just do everything together. So player one plays strategy A with probability P equals 1 over 3, and strategy B with probability 1 minus P, with probability 1 minus P, which is equal to 2 over 3. Then player 2 plays strategy X with probability Q equals 5 over 6, and strategy Y with probability 1 minus Q equals 1 over 6. And that is how that goes. So if we want to, we can now go for the expected payoff of we can now go back and maybe compute the expected payoff of player one. Okay. But I mean, the probabilities have actually given us everything we need. So we may think of the expected payoff of player one if we so wish. Okay, let me just do that as a final one. So I won't bother about the expected payoff of player two because the most important thing will be to get the probabilities. So the expected payoff of player one would be E1, which we know is 6PQ, okay, minus 5P minus 2Q plus 4. 6PQ minus 5P minus 2Q plus 4. So let's see if player one loses or not. So 6 into PQ. P is 1 over 3. Q is 5 over 6. 1 over 3, 5 over 6 minus 5p. P is 1 over 3 again. Minus 2. 2 is Q is again, Q is 5 over 6 plus 4. So this is the expected payoff of player 1. So this is 6 cancel 6. Thankfully, this is 5 over 3 minus 5 over 3. Okay. Again, minus another 5 over 3 plus 4 over 1. So yeah, 6 cancels 5 over 3, another 5 over 3. So this cancels automatically. So 2 here is 1, 2 here is 3. So we have another minus 5 over 3. So E1 is 4 over 1 minus 5 over 3. So the expected payoff of player 1 is LCM is 3. 1 in 3 is 3. 3 times 4, 12 minus 5. So the expected payoff of player 1 is 7 over 3. Okay, 7 over 3. So automatically, since it's a zero-sum game, right? Uh, so the expected payoff of player 1 is 7 over 3, and the expected payoff of player 2 is minus 7 over 3. Since the game, since the game is zero sum. So it means whatever player 1 gains, if player 1 gains, then player 2 loses. If player 2 loses, player 1 gains. Basically, that's the idea of a zero sum game. So you may want to, now go ahead and do it for the expected payoff for player 2 to confirm if this is actually correct. But this is the process to go. It's a pretty long one. So in the next video, I'll be talking about non-zero sum games. I think the issue is interpreting all the payoff matrix into the expected payoff. I think that can be pretty tricky. And don't forget, it's basically probability of playing A, that's P multiplied by getting 3, multiplied by probability that player B would also, the probability of player B to play X, and same, all that into -1 into 1 minus Q, and we set that up and do the same for, you add it up to B, and then you can go the process and go using Lagrange multiplier, and we arrive at the probabilities we have. So sign up if you have not done that already, subscribe to the channel, hit the notification bell to be sure that you don't miss any video that is uploaded here. And then, of course, comment, let me know how useful these videos are for you. And of course, let me know if there are topics you'd like me to teach or, questions you want me to solve. Then like and share so that more people can have access to this great learning. Till I come your way again, keep playing the game of life with wisdom. Bye.